In this video, we are going to develop something that is referred to as the mean value theorem for definite integrals. Now, in order to develop the mean value theorem for definite integrals, we have to go back and review the mean value theorem for derivatives. The mean value theorem is part of a standard Calculus 1 class, but you may not remember how it is stated. So I want to go back and review the mean value theorem for derivatives. And the mean value theorem for derivatives says that if a function is continuous on a closed interval from a to b, and this function is differentiable on the open interval between a and b, then we can find a magic c that lives between a and b, such that f prime evaluated at c is equal to this mess, f of b minus f of a over b minus a. Now, it's important to remember that this is just the average rate of change in the function over the interval from a to b, and this particular thing here is the instantaneous rate of change measured at x is equal to c. So measured at x is equal to the magic c value. And what I want to do is I want to find a way of applying the mean value theorem for derivatives in a Calculus 2 integral calculus context. So let's think about area accumulation functions. I'm going to let f be continuous on a closed interval between a and b, and I'm going to define a of x to be my standard area accumulation function, the definite integral between a and x of f of t dt. And just as a quick little reminder, if this is y is equal to f of x, and this is a and this is b, then at a particular x value, a of x gives that particular area. So it's important to realize that a of b is the integral between a and b of f of t dt, but that, because the variable of integration is a dummy variable, is the same thing as the integral between a and b of f of x dx. It's also important to remember that a of little a is just the area of a line segment, and the area of a line segment, of course, is 0. And these are things that I kind of want to keep in mind. There's another thing that I also want to keep in mind. I know that the fundamental theorem of calculus says that a prime of x is going to be little f of x for all the x's inside the interval in which I've defined the area accumulation function. So this is certainly going to be true in the open interval. And if you think about how the area is being swept out, the area accumulation function is also continuous on the closed interval between a and b. And so these two facts here say that the area accumulation function satisfies the hypotheses of the mean value theorem for derivatives. And I want to get that written down. What we've seen is that the area accumulation function satisfies the two hypotheses of the standard mean value theorem for derivatives. And so the conclusion of the mean value theorem holds. So the mean value theorem says there is a magic c inside the interval, inside the open interval between a and b, such that a prime at c, so a prime at c is going to be A of B minus A of A, all divided by B minus A. And now what I want to do is I want to translate this particular notation into integral notation. So I'm going to actually start by rewriting this on a new panel. So we have A prime at a magic C is equal to capital A at B minus capital A at A divided by B minus A. Now, what I want to remember is that A of x is the integral between A and x of f of t dt. So A prime at the magic C, by the fundamental theorem of calculus, is going to be f at that same C. And let me make my brackets the same color. So what we have is this side here simplifies to f of magic C is equal to. Now what I want to remember is that A of B is the integral between A and B of f of t dt, but that can be written as the integral from A to B of f of x dx, because the integral of the variable of integration is a dummy variable as long as it's not appearing as one of the two endpoints on the integral. So this chunk right here is just our definite integral from A to B. So we have the integral from A to B of f of x dx minus, well, let's see, A of A is the integral between A and A of f of t dt, and that's the area of a line segment, so that's a big fat 0. So we get a big fat 0 there, and we still have b minus a underneath here. And so the upshot is that what we've got now is that the mean value theorem for derivatives is going to imply that if f is continuous on a closed interval from A to B, and we define A of x to be equal to the area accumulation function, then we know, and I want to get just a little bit more room, then we know there exists a magic C inside my interval between A and B, so inside the open interval between A and B, such that f of C is equal to the integral between A and B of f of x dx divided by b minus a. Now this looks kind of awkward, but this statement here is often referred to as the mean value theorem for integrals. And I want to kind of state the mean value theorem for integrals that we have already proven a little bit more formally, and I also want to clean up the conclusion of it a little bit so that it's a little less awkward to look at. So very formally, we have proved this particular theorem, which is called the mean value theorem for integrals. And it states the following. If little f is continuous on a closed interval between A and B, then there exists a magic C. Let me change that color, because I want to stress that this is what we're claiming exists. There exists a magic C with A less than C and C less than B, and f of C f of C is going to be equal to the integral between a and b of f of x dx divided by b minus a. We can turn this around and multiply both sides of this by b minus a, and we can restate the conclusion as there exists a c in between a and b such that f of c times b minus a is equal to the integral between a and b of f of x dx. In the next video, we're going to look at why this is called the mean value theorem for integrals. In particular, we're going to look at the geometric meaning of this particular expression, that particular equation.